Imagine gazing up at the night sky. Stars twinkle like distant diamonds. These celestial objects are incredibly massive and powerful. They emit light and heat across unimaginable distances. How do they work? What secrets do they hold? For generations, we relied on classical physics to explain the cosmos. Yet, as we delved deeper, we encountered phenomena that defied explanation. The universe held mysteries that classical physics couldn't unravel. We needed a new understanding, a new set of laws. This is where quantum physics enters the stage. It is a revolutionary framework for understanding the universe at its most fundamental level. Our everyday experiences are governed by classical physics. We see objects move in predictable ways. These laws work well for large objects and everyday phenomena. However, these classical laws break down in the quantum realm. At the atomic and subatomic levels, the rules change entirely. Particles exhibit wave-like properties and exist in a haze of probability. Instead of having a definite position and momentum, particles have a range of possible states. This concept, known as superposition, challenges our classical intuitions. Quantum physics provides us with a new set of rules to describe the universe. These rules are often counterintuitive, but have been experimentally verified. One key insight is that energy exists in discrete packets called quanta. This idea, proposed by Max Planck, challenged the classical notion of energy as a continuous wave. Another key concept is wave-particle duality, where particles can exhibit both wave-like and particle-like behavior. These new rules have led to groundbreaking discoveries and technological advancements. Understanding these rules is crucial for comprehending the universe. They have revolutionized our understanding of matter, energy, and reality. Quantum physics can seem daunting. Its concepts are often abstract and counterintuitive. However, its importance cannot be overstated. Quantum physics is the foundation for many technologies we rely on every day. From lasers and transistors to medical imaging and nuclear energy, it has shaped our modern world. It continues to drive innovation in fields such as quantum computing and cryptography. Understanding quantum physics is about understanding the world around us. It's about appreciating the intricate workings of the universe at the smallest scales. At the turn of the 20th century, physics was undergoing a profound transformation. Classical physics faced a crisis with phenomena that defied explanation. One such mystery was blackbody radiation. Classical physics predicted an ultraviolet catastrophe, but observations contradicted this. Max Planck proposed that energy was quantized, existing in discrete packets called quanta. This hypothesis accurately explained the observed blackbody radiation spectrum. Planck's discovery marked the birth of quantum physics. It opened up a new realm of physics, challenging classical assumptions. Planck's hypothesis introduced Planck's constant, a cornerstone of quantum physics. This tiny constant relates the energy of a photon to its frequency. Planck's constant is incredibly small, highlighting quantum effects at the atomic level. In the macroscopic world, classical physics provides an accurate description. However, at the atomic scale, the quantization of energy becomes significant. Planck's discovery suggested that energy existed in discrete units. This idea challenged the classical notion of continuous energy flow. Planck's constant revolutionized physics, laying the foundation for a new era. In 1905, Albert Einstein applied Planck's quantum hypothesis to explain the photoelectric effect. The photoelectric effect refers to the emission of electrons from a metal surface when light shines on it. Classical physics predicted that the energy of the emitted electrons should depend on the light's intensity. However, experiments showed that the energy depended on the light's frequency. Einstein proposed that light could behave as a stream of particles called photons. Each photon carries energy determined by its frequency and Planck's constant. Einstein's explanation provided further evidence for the quantization of energy. It introduced the concept of wave-particle duality, challenging the classical view of light. In 1930, Niels Bohr proposed a new model of the atom. The prevailing model predicted that electrons should spiral into the nucleus, contradicting observed stability. Bohr incorporated Planck's quantum hypothesis into his atomic model. He proposed that electrons could only occupy specific, discrete energy levels. When an electron transitioned between levels, it emitted or absorbed a photon. Bohr's model explained the observed line spectra of atoms. These spectral lines provided a fingerprint of the atom's internal structure. Bohr's model introduced the concept of quantized energy levels within the atom. The early 20th century saw groundbreaking discoveries that laid the foundation for quantum mechanics. Physicists developed a mathematical framework describing particles at the atomic level. Unlike classical mechanics, quantum mechanics introduced probability and uncertainty. Heisenberg's uncertainty principle stated that it was impossible to simultaneously know both the position and momentum of a particle with perfect accuracy. Schrödinger developed a wave equation describing quantum particles as waves. The wave function provided information about the probability of finding a particle at a particular location. Quantum mechanics represented a radical departure from classical physics. It introduced a new way of thinking about the universe, emphasizing probability and uncertainty. Quantum physics challenges our everyday intuitions. The act of observation takes on a central role in shaping quantum phenomena. In the quantum realm, objects do not possess definite properties until measured. Measurement forces a quantum system to choose a particular state, collapsing its wave function. This inherent indeterminism is a key feature of quantum mechanics. It suggests a universe where chance and probability play a fundamental role. Embracing this view requires a shift in perspective. Quantum physics invites us to marvel at the strangeness of the quantum world. One of the most perplexing concepts in quantum physics is wave-particle duality. This principle asserts that quantum entities can exhibit both wave-like and particle-like behavior. The double-slit experiment demonstrates the wave-like nature of electrons. The photoelectric effect highlights their particle-like behavior. This dual nature is not a paradox, but a reflection of the limitations of our classical categories. Quantum entities exist in a superposition of states, exhibiting both characteristics until measured. Wave-particle duality has profound implications for our understanding of reality. It suggests a universe where matter and energy exist in a more fluid and interconnected state. The double-slit experiment vividly demonstrates the wave-like nature of matter. A beam of electrons is fired at a barrier with two slits. Instead of two bands, an interference pattern appears, showing alternating bright and dark fringes. Each electron acts as a wave, passing through both slits simultaneously. This creates two wave fronts that interfere with each other. The bright fringes are regions of constructive interference. The dark fringes represent destructive interference. Even one electron at a time, the pattern builds up, showing wave-like behavior. This experiment highlights the inherent strangeness of the quantum world. Another cornerstone of quantum physics is Heisenberg's uncertainty principle, formulated by German physicist Werner Heisenberg in 1927. This principle states that it is impossible to simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely one measures the position of a particle, the less precisely one can determine its momentum, and vice versa. This uncertainty is not due to limitations in our measurement techniques, but rather a fundamental aspect of the quantum world arising from the wave-particle duality of matter. Imagine trying to pinpoint the exact location of a ripple on a pond. As you try to confine the ripple to a smaller region, its momentum or the speed and direction of its propagation becomes more uncertain. Similarly, in the quantum realm, confining a particle to a smaller region of space inherently makes its momentum more uncertain. This uncertainty principle has profound implications for our understanding of the nature of reality. It suggests that at the most fundamental level, the universe is not a collection of objects with definite properties, but rather a web of interconnected possibilities. The uncertainty principle also has practical implications, particularly in the realm of quantum technology. For instance, it sets a fundamental limit on the precision of certain measurements, such as those involved in quantum computing and cryptography. One of the most intriguing consequences of quantum mechanics is quantum tunneling, a phenomenon that allows particles to pass through energy barriers that would be insurmountable according to classical physics. Imagine rolling a ball up a hill. Classically, if the ball doesn't have enough energy to reach the top, it will roll back down. However, in the quantum world, there's a small but finite probability that the ball could tunnel through the hill and appear on the other side. This counterintuitive phenomenon arises from the wave-like nature of particles. In quantum mechanics, a particle is represented by a wave function, which describes the probability of finding the particle at a particular location. When a particle encounters an energy barrier, its wave function doesn't abruptly end at the barrier, but rather extends into the forbidden region. If the barrier is thin enough, there's a chance that the wave function will extend to the other side, meaning there's a non-zero probability of finding the particle beyond the barrier. This phenomenon, though seemingly impossible from a classical perspective, has been experimentally verified and has significant implications for various fields. For instance, quantum tunneling plays a crucial role in nuclear fusion, the process that powers the sun. It also forms the basis of technologies like scanning tunneling microscopes, which allow scientists to image surfaces at the atomic level. Another mind-bending concept in quantum mechanics is quantum superposition, which states that a quantum system can exist in multiple states simultaneously until a measurement is made. This is not merely a matter of our ignorance about the system's true state, but rather a fundamental aspect of the quantum world. Imagine a coin standing on its edge, spinning rapidly. Until it falls and reveals either heads or tails, it exists in a superposition of both states simultaneously. Similarly, a quantum system before measurement exists in a blurry combination of all possible states, each with a certain probability. This superposition principle has profound implications. It suggests that at the quantum level, reality is not a collection of definite objects with fixed properties, but rather a web of interconnected possibilities. It also forms the basis of quantum computing, where quantum bits or qubits can exist in a superposition of 0 and 1 states, allowing for exponentially faster computation compared to classical computers. Embracing the concept of quantum superposition requires a shift in perspective, a willingness to accept that the quantum world operates under different rules than our everyday experience. It's a world where the both and logic prevails, where possibilities coexist until a measurement forces a definite outcome. Throughout the history of science, experiments have played a pivotal role in shaping our understanding of the universe. They serve as the ultimate test of our theories, providing empirical evidence that either supports or refutes our models of reality. In the realm of quantum physics, where the laws of nature often defy common sense, experiments have been particularly crucial in revealing the bizarre and counterintuitive behavior of the quantum world. From the double-slit experiment, which demonstrated the wave-particle duality of matter, to the Bell test experiments, which confirmed the non-local nature of quantum entanglement, these groundbreaking experiments have not only validated the predictions of quantum mechanics, but also challenged our fundamental assumptions about the nature of reality. They have forced us to confront the limitations of our classical intuitions and embrace a new quantum worldview. These experiments are not mere laboratory curiosities, but rather profound demonstrations of the fundamental principles that govern the universe at its most fundamental level. They provide a glimpse into a realm where particles can be in multiple places at once, where information can travel instantaneously across vast distances, and where the very act of observation can influence the outcome of events. In this section, we will delve into some of the most pivotal experiments in quantum physics, exploring their historical context, experimental setup, key findings, and implications for our understanding of the quantum world. The double-slit experiment, first performed with light in the early 19th century and later with electrons and other particles, stands as a cornerstone of quantum physics, vividly demonstrating the wave-particle duality of matter and the inherent strangeness of the quantum world. In this experiment, a beam of particles, such as electrons, is fired at a barrier with two narrow slits. Behind the barrier, a detector screen records where the particles hit. If particles behaved solely as tiny, localized objects, we would expect to see two distinct bands on the detector screen, corresponding to the two slits. However, the experiment reveals a much more intriguing pattern. Instead of two bands, a series of alternating bright and dark fringes appears on the screen, an interference pattern characteristic of waves. This interference pattern arises because each particle, acting as a wave, passes through both slits simultaneously, creating two wavefronts that interfere with each other. The bright fringes correspond to regions of constructive interference where the wave crests align, while the dark fringes represent destructive interference where crests and troughs cancel each other out. What makes the double-slit experiment even more astonishing is that the interference pattern persists even when the particles are fired one at a time. This implies that each particle somehow interferes with itself, as if it's passing through both slits simultaneously. Furthermore, if we try to determine which slit each particle goes through by placing a detector at one of the slits, the interference pattern disappears, and we observe the classical two-band pattern. This observation highlights the crucial role of measurement in quantum mechanics. The act of measuring which slit the particle goes through forces it to choose a definite path, destroying its wave-like nature and collapsing its wave function into a particle-like state. This experiment, with its simple yet profound implications, has captivated physicists and philosophers for decades, forcing us to confront the limitations of our classical intuitions and embrace the bizarre yet fascinating nature of the quantum world. Quantum entanglement links two particles sharing the same fate regardless of distance. Einstein called it spooky action at a distance. Imagine flipping two coins simultaneously. Classically, they are independent events. In quantum physics, entangled particles' properties are correlated. Measure one particle's spin, and you instantly know the others. This challenges the principle of locality. Einstein, Podolsky, and Rosen proposed the EPR paradox. John Bell's inequalities tested these ideas. Experiments confirmed quantum entanglement's non-local nature. This has profound implications for quantum technologies, including quantum computing, communication, and cryptography. In 1964, physicist John Bell formulated Bell's theorem, revolutionizing our understanding of reality. Bell's theorem challenged the concept of local realism, a view held by Einstein. Bell derived inequalities to test if local realism held true. Experiments have consistently violated Bell's inequalities. This suggests the universe is non-local or realism is an illusion. Bell's theorem remains a testament to human ingenuity. In the quantum world, observation can freeze time. The quantum Zeno effect shows that continuous observation can inhibit a quantum system's evolution. Imagine a radioactive atom poised to decay. Continuous measurement collapses its wave function, freezing its state. This effect has applications in quantum computing and other technologies. Observation actively shapes the quantum world. For much of the 20th century, quantum physics remained largely confined to the realm of theoretical physics, its bizarre predictions captivating the minds of physicists, but seemingly far removed from practical applications. However, as our understanding of the quantum world deepened, so too did our ability to harness its power for technological advancements. Today, quantum technologies are emerging as a transformative force, poised to revolutionize fields as diverse as computing, communication, sensing, medicine, and material science. From quantum computers capable of solving problems intractable for even the most powerful classical computers to quantum communication networks that promise unbreakable encryption, quantum technologies are pushing the boundaries of what's possible, opening up new frontiers in science, engineering, and beyond. These technologies leverage the counterintuitive properties of the quantum world, such as superposition, entanglement, and tunneling, to achieve unprecedented levels of performance, sensitivity, and security. Quantum technologies are no longer a futuristic dream, but rather a rapidly developing reality with the potential to reshape our world in profound ways. In this section, we will explore some of the most promising quantum technologies, delving into their underlying principles, current state of development, potential applications, and challenges that lie ahead. Imagine a computer so powerful it could solve problems in seconds that would take classical computers billions of years to crack. This is the promise of quantum computing, harnessing quantum mechanics to perform calculations at unimaginable speeds. Quantum computers use qubits which can exist in multiple states simultaneously, allowing for exponential efficiency. They exploit phenomena like entanglement and interference to perform parallel computations, leading to breakthroughs in fields like medicine, finance, and AI. Despite challenges, rapid advancements and investments are heralding a new era of computing power. Section 3, Quantum Cryptography, Unbreakable Secrets. In an age of digital communication, securing sensitive information is paramount. Quantum cryptography offers unbreakable encryption, leveraging quantum mechanics. Unlike classical cryptography, it uses the laws of physics. Quantum key distribution, QKD, is a promising approach. QKD ensures secure key sharing by collapsing wave functions. Any eavesdropping attempt disturbs the quantum state, alerting parties. This makes quantum cryptography a game changer. It can revolutionize banking, government, and healthcare. While still early, quantum networks are being tested globally, paving the way for secure communication by nature's laws. Section 4, Quantum Sensing Precision Beyond Imagination. Imagine sensors so sensitive that they could detect minute changes in gravity, magnetic fields, or time with unprecedented precision. This is the potential of quantum sensing, a rapidly developing field that exploits the exquisite sensitivity of quantum systems to measure physical quantities with extraordinary accuracy. Quantum sensors leverage the unique properties of quantum systems, such as superposition and entanglement, to achieve sensitivities far beyond what's possible with classical sensors. For instance, atomic clocks, the most precise timekeeping devices ever created, rely on the quantum properties of atoms to measure time with astonishing accuracy, losing less than a second every few 100 million years. Other types of quantum sensors are being developed to measure magnetic fields with nanoscale resolution, detect gravitational waves, and even image the human brain with unprecedented detail. Quantum sensing has the potential to revolutionize various fields, including medicine, navigation, geology, and fundamental physics. For instance, quantum sensors could be used to develop new medical imaging techniques that are safer and more precise than existing methods, create more accurate GPS-free navigation systems, detect underground resources with greater accuracy, and even test the fundamental laws of physics with unprecedented precision. As the field of quantum sensing continues to advance, we can expect to see a new generation of sensors that will push the boundaries of measurement, enabling us to probe the world around us with unprecedented detail and sensitivity. Section 5, Quantum Biology, Life's Quantum Secrets. Life, in all its diversity and complexity, has long been a source of wonder and inspiration. While classical biology has made remarkable progress in unraveling the mechanisms of life, some biological phenomena seem to defy explanation solely through classical lens, hinting at the possibility that quantum mechanics may play a more significant role in the processes of life than previously thought. Quantum biology, an emerging field at the intersection of quantum physics and biology, seeks to explore the potential role of quantum mechanics in living systems. From the efficient energy transfer in photosynthesis to the navigation of birds using Earth's magnetic field, there are growing indications that quantum phenomena may be at play in various biological processes. For instance, recent studies suggest that quantum coherence, the ability of quantum systems to maintain synchronized states, may play a role in the efficiency of photosynthesis, allowing plants to harvest light energy with remarkable efficiency. Other studies are investigating the potential role of quantum entanglement in the avian compass, which enables birds to navigate across vast distances using Earth's magnetic field. Quantum biology is still in its infancy and much remains to be explored and understood. However, the tantalizing possibility that quantum mechanics may underpin some of life's most essential processes is driving further research and exploration, potentially leading to new insights into the very essence of life itself. As we stand on the precipice of a new technological era, quantum physics is no longer a mere theoretical curiosity confined to the halls of academia. It's the driving force behind a technological revolution that promises to reshape our world in profound ways. The quantum horizon beckons with tantalizing possibilities, from quantum computers capable of cracking the codes of nature to quantum communication networks that could render eavesdropping obsolete. Imagine a world where diseases are diagnosed and treated with unprecedented precision, where new materials with extraordinary properties are designed atom by atom, and where the secrets of the universe are unlocked through simulations that harness the full power of quantum mechanics. This is the promise of the quantum revolution, a revolution driven by our deepening understanding of the universe at its most fundamental level. But the quantum horizon is not without its challenges. Building large-scale, fault-tolerant quantum computers, for instance, remains a formidable task, requiring overcoming significant technical hurdles. Similarly, understanding the role of quantum mechanics in biological systems where complexity reigns supreme is a daunting yet exhilarating challenge. Yet the potential rewards are too great to ignore. Quantum computing, with its promise of exponential speed-ups for certain types of problems, is poised to revolutionize fields as diverse as medicine, materials science, finance, and artificial intelligence. While still in its early stages of development, quantum computing has already made significant strides, with prototypes demonstrating the potential of this revolutionary technology. One of the key milestones in the development of quantum computing is achieving quantum supremacy, the point at which a quantum computer can outperform even the most powerful classical computers for a specific task. This milestone, once considered decades away, is now within reach, with several research groups around the world racing to demonstrate quantum supremacy. Beyond quantum supremacy, the next frontier in quantum computing lies in building large-scale, fault-tolerant quantum computers, capable of tackling real-world problems. This will require overcoming significant technical challenges, such as improving qubit stability, developing efficient error correction codes, and scaling up the number of qubits in a quantum computer. Despite these challenges, the field of quantum computing is brimming with optimism, fueled by rapid technological progress and significant investments from governments and private companies alike. The era of quantum computing is dawning, and with it comes the potential to unlock solutions to some of humanity's most pressing challenges. For centuries, biologists have sought to unravel the secrets of life, peering into cells with ever-increasing magnification, seeking to understand the intricate mechanisms that govern living organisms. While classical biology has made remarkable progress in explaining the machinery of life, some biological phenomena seem to defy explanation solely through the lens of classical physics. From the efficiency of photosynthesis, where plants capture light energy with near-perfect efficiency, to the mystery of the avian compass, which allows birds to navigate across continents using Earth's magnetic field, there are hints that quantum mechanics may play a more significant role in biology than previously thought. Quantum biology, an emerging field at the intersection of quantum physics and biology, seeks to explore these tantalizing possibilities. Researchers are investigating how quantum phenomena like coherence, entanglement, and tunneling might be exploited by living organisms to gain an advantage in their respective environments. For instance, studies suggest that quantum coherence may play a role in the efficiency of photosynthesis, allowing plants to transfer energy from light-harvesting molecules to reaction centers with minimal loss. Other studies are exploring the potential role of quantum entanglement in the avian compass, proposing that entangled electron spins within bird eyes could act as sensitive magnetic sensors. While quantum biology is still in its infancy, its potential to revolutionize our understanding of life is immense. Quantum mechanics and general relativity are fundamentally incompatible. This clash has puzzled physicists for decades, leading to a quest for a unified theory of quantum gravity. String theory and loop quantum gravity are promising approaches. This quest could revolutionize our understanding of the universe. Our journey through the quantum world, from its humble beginnings in the study of black-body radiation to the mind-bending concepts of entanglement and superposition, has revealed a universe far stranger and more wondrous than we could have imagined. Quantum physics, with its counterintuitive laws and probabilistic interpretations, has challenged our classical intuitions, forcing us to confront the limitations of our everyday experience in comprehending the universe at its most fundamental level. We've seen how the very act of observation, once considered a passive process, takes on a central role in shaping quantum phenomena, collapsing wave functions, and determining the fate of particles. We've marveled at the dance of entanglement, where particles linked across vast distances share a destiny that transcends the limitations of space and time. And we've glimpsed the potential of quantum technologies to revolutionize our world, from quantum computers capable of cracking the codes of nature to quantum sensors that promise to unveil the universe's hidden secrets. The quantum revolution is not merely a scientific revolution, it's a revolution in thought, a paradigm shift that compels us to reconsider our place in the grand tapestry of the cosmos. As we venture further into the 21st century, the quantum revolution is gathering momentum, its impact rippling across scientific disciplines and technological frontiers. Quantum technologies, once relegated to the realm of science fiction, are rapidly becoming a reality, promising to transform fields such as medicine, materials science, communication, and artificial intelligence. Imagine a world where diseases are diagnosed and treated with unprecedented precision, where new materials with extraordinary properties are designed atom by atom, where secure communication is guaranteed by the very laws of physics, and where the mysteries of the human brain are unlocked through simulations that harness the full power of quantum mechanics. The quantum future beckons with a tapestry of possibilities, each more awe-inspiring than the last. But the quantum future is not without its challenges. As we develop increasingly powerful quantum technologies, we must also grapple with the ethical and societal implications of wielding such power. How do we ensure that these technologies are used for the benefit of humanity and not for harm? How do we navigate the philosophical questions raised by quantum mechanics, which challenges our very understanding of reality? These are questions that will require careful consideration and dialogue as we embark on this exciting new era of scientific exploration and technological innovation. The quantum future is not predetermined, but rather a canvas upon which we, armed with our knowledge and guided by our values, have the opportunity to paint a brighter future for all. As we venture into the 21st century, the quantum revolution is gathering momentum, its impact rippling across scientific disciplines and technological frontiers. Quantum technologies, once science fiction, are becoming reality, promising to transform fields like medicine, materials, science, communication, and AI. The quantum future beckons with possibilities, each more awe-inspiring than the last.